This is our second webinar. It's going to be on indoor air quality and UV disinfection. Indoor air quality can affect both health and employee performance. IAQ can be affected by elevated CO2 levels, and it is regulated by codes and standards. IAQ can be affected by odors and contaminants, such as volatile organic compounds and dust particulates. IAQ can also be affected by allergens. We have insect allergens, fungal allergens, bacterial allergens. We have dog dander and cat dander and a variety of other things in the air. Airborne pathogens and allergens. Pathogens are the greatest threat to human health, but allergens also affect health and employee productivity. Large fungal spores tend to be allergens, but these are easily removed by filters. And this is why filters are often so effective against allergies. Fungal spores are less susceptible to ultraviolet light. However, the pathogens, bacteria, and viruses are fairly easily removed by ultraviolet light, and many are also removed by filters. The fungal pathogens tend to be large, and most of the fungi that you see here in this graph are in fact allergens, and there's a number of pathogens in here as well. Most of the bacteria and viruses are true pathogens. We can have airborne and surface-borne contamination in buildings, and they are interrelated problems. Airborne microbes, particularly the large fungi and bacteria, will tend to settle downwards at rates that depend on their aerodynamic diameter. The settling will primarily be on horizontal surfaces, although there can be some attraction to the vertical surfaces as well. Viruses, depending on their size, can remain airborne almost indefinitely. The classic example is now SARS coronavirus. Surface-borne microbes, even though they settle on horizontal surfaces, are not fixed to those surfaces, and the slightest movement, vibration, or sound is capable of knocking them back up into the air. The activity of walking on floors is actually like stepping on a drum or hitting a drum, and it pops those viruses back into the air, from where they continue to travel or may continue to settle. Disinfecting with the air with the UV has been shown to reduce levels of surface contamination. And this is clearly because many of the microbes on surfaces have settled there from the air. The persistence of microbes on surfaces is surprising. Microbes can last anywhere from a few minutes to a few days, weeks, or even months. Some of the major pathogens in healthcare include pathogens like Clostridium difficile or Clostridioides difficile. It can last over 100 days on surfaces, and it makes it very difficult to eradicate. And many of the other microbes, such as MRSA, can last extended periods of time in the indoors. And typically, they will settle to surfaces and remain on those surfaces. Hospital-associated pathogens. We don't see allergens among hospital-associated infections. We just see the pathogens, primarily bacteria. These are examples of all the bacteria that are primary causes of infections in hospitals. And among these, we see Staph aureus or MRSA, Pseudomonas, Streptococcus, and many others. The frequency of pathogens in hospital environments is shown here in the typical annual cases. We can see we can have several million of influenza virus. This chart needs to be updated because SARS coronavirus is now the #1 hospital nosocomial infection, and it would sit way up here above influenza. Okay. Ultraviolet air and surf disinfection can both contribute to lowering building bioburden and improving IAQ. Reducing the building bioburden reduces airborne concentrations. That is to say, removing microbes from all the surfaces that they contaminate will simultaneously reduce airborne concentrations. And of course, reducing airborne concentrations will also reduce surface concentrations. So surface and air disinfection technologies are complementary approaches to cleaning up your building and lowering your building bioburden. Lowering the bioburden in any building should reduce infections, should reduce allergy symptoms, etc. And of course, filters are essential to improve overall performance, and I will show why that is later. Now, UV can also control VOCs and odors. And ultraviolet light, abbreviated UVL, I'm introducing this acronym as IUVA, may be using this acronym UVL to replace all the current terms for UV, such as UVGI, GUV, and UVG. We're trying to standardize the terminology so there's less confusion. So this may be the first time you see the use of UVL. Broadband UV light, ultraviolet light, can generate hydroxyl radicals and ozone, which rapidly oxidize a wide range of indoor odor-producing compounds, like ammonia, hydrogen sulfide, and mercaptans. But ozone is not desirable, but it also can be removed from the airstream. Narrowband UVC at 254 can break a number of chemical bonds, including proteins and immunoglobulins in allergens, without generating ozone. Some aromatics or volatile organic compounds can be directly destroyed by UVC. UV has the potential to destroy allergenic compounds, both in air and on surfaces. Proteins can be activated by ultraviolet light. Ultraviolet light is absorbed by proteins, and this results in denaturation and decomposition of those proteins. And those may be proteins that are part of allergens. Ultraviolet light can break down allergens via photooxidation or photolysis. UV exposure initiates free radicals and catalyzes other stages of oxidation. UV photooxidation causes progressive degradation of collagen molecules. UV can also induce free radical formation, and this itself will cause reactions with VOCs and other airborne odors. The end result of UV is the degradation of protein molecules into smaller molecular fragments and photopolymerization. VOCs and odor removal with UVC. A higher frequency of UV light, called vacuum UV, below about 200 nanometers, can destroy odors by photolysis. Vacuum UV may not travel far in air, but it may travel far enough to react with VOCs. This frequency of light produces oxidizers that actively eliminate VOCs and odors within an exhaust duct system. The Sanuvox Grow Saver is designed for this application. It can eliminate odors. Maintenance is normal, and there is no costly change out of carbon filters. Now, in the inactivation of microorganisms, survival curves can be modeled as two-stage exponential decay curves, as shown on the right here in the example of E. coli. We typically get a first stage of rapid decay, after which we hit a survival curve, or a second stage in the survival curve, at which it responds much more slowly to the UV dosing. The tails that we see in these curves are generally artifacts of the preparation process as a result of clumping, high concentrations, or the exact mixture used, or even the substrate. We can create tails in laboratory experiments as artifacts of the disinfection process. They typically manifest about 3 to 4 log reduction. Now, in theory, the susceptibility of any microbe is an intrinsic property of the DNA or RNA, after accounting for other physical factors such as size or humidity. And the first stage rate constant is the true intrinsic rate constant of the microbe. And as I've said, the tail is an artifact. There are human pathogenic viruses there's a very large number of these. I could only show about 100 on this chart here. I'm showing all the viruses on this chart for which we know the ultraviolet sensitivity, but the ones here for which we don't have been recomputed using genomics, genomic predicting models. We can see down in here that the adenovirus, which is a big problem in water disinfection, sits up at the high end of resistance at about 40 to 100 millijoules per square centimeter. But most of the viruses sit well under 40 millijoules per square centimeter, which is a reasonable dose to achieve in indoor systems. The SARS virus, coronavirus, turns out to be the weakest of all the viruses. It sits down in the lower corner. Now, we also have human pathogenic bacteria. And by the way, both of these charts are available in large size posters that you can get from logging on to sanuvox.com. The bacteria overall are a bit less susceptible to ultraviolet light, or a bit more susceptible to ultraviolet light. And we can see this in the cutoff at 40 millijoules per square centimeter. Will virtually cover all bacteria, sufficient dose for all bacteria. But some of these bacteria up here are spores, which are better removed by filters. Therefore, a dose of somewhere around 10 millijoules per square centimeter would virtually cover 99% of bacteria other than spores. There have been many field trials and lab tests on ultraviolet light air disinfection, beginning in 1925 with the use of UV for air disinfection in laboratory tests. The first upper room systems, which were a little more than naked UV lamps, were placed in schools in 1938. In 1939, it was found that induct air disinfection could remove 99% of bacteria at least. UV has been applied to air conditioning systems. It's been used in military barracks in both the form of upper room and lower room systems. It's been used in nurseries to reduce infections. And it was proven in '57 to be very effective at removing tuberculosis, airborne tuberculosis. They've used UV units to control infections in isolation units. In 1993, Dion showed that airborne bacteria could be reduced by airborne disinfection systems using UV. Unitary UV systems removed up to 99% of airborne TB in a 1997 study. And Menzies showed in a watershed study, the first application in a large commercial building, reduced respiratory symptoms. Now, there are at least 4 types of UV technologies that can be applied for air disinfection in buildings. There is induct UV, and there is portable UV systems. These are virtually identical in terms of performance or performance characteristics. The induct UV system will typically sit outside the room or in a mechanical equipment room. The portable UV system might sit directly inside the room. They are both characterized by an airflow and an efficiency, and that efficiency is measured across the unit from point A, the inlet, to the outlet. In both cases, portable UV and induct. For any given volume UV, we can compute the air changes per hour. And for these two systems, our equivalent air exchange in terms of outside air equivalent is simply the efficiency times the air change rate. We have another system that's very common, the upper room system. It too will have an airflow. It too will have a measurable efficiency. It can be applied in a volume. However, the air change rate per hour does not necessarily define the equivalent outside air. This is a matter that depends on your performance test results. We have to compute REACs based on performance test results. And there are two types of tests, the type 1 and a type 2. The type 1 is typically used for induct and portables, and the type 2 test is typically used for upper rooms, can be used for whole rooms, and can also be used for portable units. And finally, we have a whole room UV system. Typically, whole room UV has been used to disinfect surfaces in rooms, but it acts simultaneously to disinfect the air. There is at least one published test result showing whole room UV performance under these conditions. It too will have an equivalent air exchange, which may be higher than the actual recirculation airflow, and these values can be determined as a result of the performance test results. Induct air UV disinfection systems are highly effective. The EPA test performed in 2006 showed at least a 99.9% reduction. They're almost virtually 100% removal of most pathogens. They are simple to install, very cost effective compared with other technologies, and they combine very well with filters, particularly the MERV 13 filter recommended by ASHRAE. Upper room UV systems are common. They are UV units, which are collimated beams put in the upper part of any room or clinic or classroom. They're designed to disinfect the air in the upper room and through complete mixing, clean out the air in the entire room. There's an extensive body of supporting research showing their effectiveness as well as showing their safety. Cooling coil disinfection is not technically air disinfection. However, cooling coil disinfection systems, which can save a lot of energy and cost of operation, prevent re-entrainment of filtered pathogens or captured pathogens by removing mold, mildew inside air handling units and on cooling coils. They remove sources of odors. But because they are so short, have such a short exposure time, they have a limited effect on air disinfection. They contribute to air disinfection, but by themselves do not disinfect the air completely. Whole room UV air disinfection systems, which we mentioned. Currently, there are proposals for developing whole room UV air disinfection systems using far UV, which is presumably harmless to humans, although that remains to be seen or proven conclusively. But if such was the case and we can employ far UV inside rooms, it still has to be approved by the regulatory agencies. However, the initial results suggest that it works very well. There are also standalone units, portable units for air disinfection. In the event that a building cannot retrofit sufficient air changes, they can always place portable units inside rooms. These can be placed in rooms to control the local sources. Standalone units may be equipped with HEPA filters, MERV filters, and UV systems. They typically remove 99.98% of indoor contaminants or more. At least that is the HEPA filter models. The MERV filter models with UV also remove extremely high rates of pathogens and allergens. Now, surface disinfection is typically performed with what we call tower units, like this example ASEP 2X. Surface disinfection is essential in healthcare, and many hospitals use these surface disinfection systems or adopted them during the coronavirus pandemic to clean their operating rooms, to clean their patient rooms after they were evacuated by the patients. Typically, surface disinfections can remove anywhere from 90 to 99.99% of surface-borne contaminants. These systems operate by direct line of sight. They can do nothing for shadowed areas, but as long as there is direct line of sight on a surface, the surface will be highly disinfected. These systems can only be applied after the rooms are wiped clean with hospital disinfectants per healthcare protocols. UV does not penetrate plasma, blood, or other surface soilage very well. Therefore, that visible soilage must be removed. And that is what healthcare workers do when they clean a room. If they can see soilage, they will wipe it clean. So UV is only intended to be used on visibly clean surfaces in hospitals. And when it's applied in that fashion, it is very effective. UV is also used in water disinfection, but in water, microbes tend to be more resistant for reasons that have to do with attenuation of UV in water. Microbes on surfaces tend to be a little more resistant than microbes in water, and this is because they are sitting still. Microbes that are in air are rotating and spinning and diffusing in every direction. They are being exposed on all sides by UV, and we call this multi-vector light. When light is provided from multiple directions on a spherical microbe, the kill rate is faster and you get higher kill rates as a result of multi-vector light. And this tends to explain most of the effect of UV in air. It can produce high reductions of UV of microbes in air, particularly viruses, as opposed to water or surfaces. This is true for viruses. Both low and high RH don't make a difference. This is not true for bacteria, where the relative humidity makes a difference. UV induct disinfection units are tested according to typical standards. We have standards from EPA, ANSI, ASHRAE, and ISO, which provide a disinfection efficiency and airflow measurements in a tested system. This is an induct test where they measure from the inlet to the outlet, and they measure the airflow and the disinfection efficiency. One of the tests, ISO, also measures the UV dose, but the UV dose is rather redundant to the other parameters, efficiency and airflow. The disinfection and efficiency and the airflow pretty much tell you everything you need to know about the system. Systems like upper room systems are tested using steady state testing, where they inject a source into a room. They take a sample point and they measure the difference when the UV is turned on or off. It's a very effective kind of test, a very ancient type of test that has been used. It's called a model room test. We have standards from ASTM, ASHRAE, and others that use model rooms, and these model room tests measure, again, the disinfection efficiency and the airflow. Once we know these parameters, we know pretty much everything we need to know about the operation of these systems, and it becomes less important to measure the dose or the irradiance. Here's an example of the ASTM test setup. They have a model room of 50 cubic meters, I believe it was supposed to be, and they inject a source and they take air samples, and from this they determine the steady state condition. When you inject a source of contaminants into a room, the concentrations will climb until you reach some steady state condition. If there is no air cleaning technology, the steady state condition will be reached when the natural die-off of the microbes equals the input or source rate. We're showing here outside air, 15% outside air, which is typical for most buildings in the world today. We can see that in 8 hours, it has not reached steady state because it has not leveled off. Outside air at 15 ACH is not adequate to keep your building air clean. In fact, if you're in a building with natural ventilation, which amounts to about 15% outside air, the levels will climb continuously throughout the day. And you can imagine what this means during the coronavirus epidemic. If you're in a non-ventilated room with other people, those levels are just climbing and climbing all day. Now here we put in an upper room system and we keep the 15% outside air, and the upper room system goes to steady state within 2 or 3 hours. If we use only a filter, and the filter is designed in this case to remove the subject microbe, I think it was either TB or Serratia, we get a steady state at an even lower condition than the upper room system. And if we use induct UV operating at 99.9% efficiency, we get the lowest steady state condition of all. Now, performance measurement of UV systems gives us airflow and removal efficiency. Whether you look at test type 1 on an induct system, or you look at test type 2 in a model room, the end result of the performance testing is the two values of removal efficiency and airflow. Once we know the removal efficiency and the airflow from the test data, it's possible to compute the equivalent air changes of outside air that system will match. Now, the importance of equivalent air changes is probably going to be realized very soon, thanks to ASHRAE standard 241P, as it allows for the use of EAC technologies, or technologies which provide equivalent air changes. And since most buildings do not meet the current guideline for air exchange, which according to ASHRAE is about 5 to 6 air changes per hour for commercial buildings. Most buildings will not have that capacity presently. And for them to install an additional 4 air changes per hour is a big problem for the ductwork, for the air handling unit, the fans, the motors, even the cooling coils and the heating coils will be affected. Therefore, it may be a very expensive proposition to simply add airflow to your building. It is likely much more economical to add UV technologies or filtration to make up the difference in the EAC. As long as we have the airflow and the efficiency, we can compute the equivalent air changes, and that allows us to do performance comparisons between equipment and, of course, the all-important economic evaluations. Which of these technologies is most economical for your building? And of course, we can then look at quantitative risk assessment to decide how much protection we really need, and this also factors into the economics of any system we buy. Now, again, I want to reiterate that combining UV infiltration is optimum. You get an optimum removal of all pathogens across the entire area of pathogens, from fungal spores to small bacteria. The ASHRAE has recommended a MERV 13 filter. A MERV 13 combined with a UV system producing a typical 99.9% against some target microorganism will give you the greatest removal rates, and possibly at the lower cost, though this remains to be seen and evaluated. It's a simple matter to combine filters and UV in series. And when UV is combined with MERV 13 filters, we get optimum removal rates for bacteria, fungi, and viruses. This is a breakdown showing in the blue and green, UV removes close to 100% of bacteria. The ones that are not removed are easily handled by the MERV 13 filter. And for viruses, again, we remove close to 100% of all viruses, and the ones that are large or in the most penetrating particle size range or may be removed by filters, even if they are in the most penetrating particle size range. Now for fungi, it's a mixed bag. The fungi tend to be very large and so are easily removed by the filter, and what remains can be inactivated by UV. Okay, I've just about used up my allotted time, and I will be happy to take any questions on the preceding material or any questions in general if you have them. Thank you very much. I will return the screen.
Any questions? You can, yes, give me a second. Go ahead, please. Oh, sorry.
Yeah. I see one question. Should I just pick these up here? Okay, let's see. Shashi Jacob. Did you have your hand raised? Okay.
Okay, now I think I can.
Perfect.
Can I?
Go ahead.
Okay. Oh, thank you, Mr. Kowalski. It was a nice presentation. I have actually, I don't know, I have a time. I have three questions.
Okay.
So the first thing is, if we are introducing your induct UVC system in HVAC, what is the possibility of a rise in temperature due to UV lamps? Because I'm basically from India, and it's a southern part. Here we have a high relative humidity, and recently in our summertime, it was reached something around 40 degrees Celsius. So I heard something from my customer that this is they feel a little bit warm after they have switched on their UV lamps. So what is your opinion about this?
Yeah, well, UV lamps are about 31% efficiencies. So about 69% of your electrical energy is going to end up as heat. Since a UV induct system might typically use, it's hard to say, anywhere between 40 to 100 watts or more, possibly a few hundred watts, you can calculate how much heat is being added to your system. There's not a lot you can do. In most buildings, that would be a very negligible amount of additional heat. But in hot climates, I could see small buildings, it might make a difference. There's not too many good options. One is to consider Teflon shields on the lamps to reduce heat transfer, or quartz shields like they use in water disinfection to reduce the heat transfer. And another option, which I think is not currently used, is to place the UV lamps outside the duct with a quartz window and just shine the light in there and not dump any heat. Hardly any heat would go into the duct. Those are the only suggestions I have for you.
Okay, nice. So can I ask one more question? Excuse me.
Yes.
Okay.
Yes.
Something that one is connected with water disinfection. I think I have saw one of your slide mentioned about the water disinfection. Yeah. In normal case, turbulent or laminar flow is more effective for a water disinfection.
In my opinion, a turbulent flow would be more effective because the effect is to approach complete mixing in water. And as long as you get more water mixing up against the surface of the lamp, you will get the highest dosing possible, as opposed to laminar flow where there's very little mixing. If there was truly laminar flow, you would get almost no mixing, and you would get no mixing, and you would get limited dosing into your water stream. So I don't know if that's clear or not, but I'm basically turbulent flow is better. The more mixed the air.
Yeah. Thank you. I think I understood. It is interesting. May I ask a very wonderful question, please?
Yes.
Okay. This is connected to the low pressure lamps that you are using. So if you are using it in your lamp in a cold chain services, I think it's a mercury pressure and the output is connected with the ambient temperature. If you are using your lamps in 0 to 5 degrees Celsius that we are normally using for preserving the vegetables and fruits in cold chain application. So how we will rectify? Because I could see that when the efficiency of the UV lamp is drastically down at a low temperature. So how we can overcome this, and what is the solution and the suggestion from your side, sir?
Yeah, low temperature air will reduce the output of the lamp. The lamp needs to stay hot to output at peak efficiency. Therefore, we don't recommend operating lamps in cold environments because the efficiency is so low, it renders the system near worthless. The options for keeping lamps warm are similar to the options for keeping lamps cool in hot climates. You could shroud them with a Teflon shield or a quartz glass shield to insulate them against the cold and allow them to get hot. Those are about the only options. Designing UV lamps for cold environments is a challenge and it's a problem. If nothing else works, you have to increase the wattage to very high levels to get all the energy you need into that environment. Yeah, I understand that's a new application, UV disinfection of refrigerated items. It's an engineering challenge that's going to have to be looked at in every case.
Yeah, yes, sir. It's really a challenging. I understood that. Okay, thank you. I don't know, the coordinator is recommending I don't know, some other people, they may ask a question. I don't know whether I can ask one more question if you permit, then I'll wait.
I would let you ask one more question.
This is my last question. This is my last question, sir. Okay. That something is connected, we are facing a problem, because I could see that one in similar, you see that room type, I would say something like a standalone systems, that freestanding device. That type, it's okay. You have mentioned in slide, there is something FERV13, MERV13 filter and some UVC lamp together. So what is the possibility of, because in southern part, I belongs to Kerala, that's a state, the southern part. Here it's a humidity is very high. It is noticed that there are a lot of fungus and bacteria are deposited on the backside of the filter you are talking about. Yeah. So in this case, this is a portable device. If I am moving this, normally I could see that the people are bringing that one from one room to another room, this type of portable devices. So what is the possibility of getting back this, all the deposited virus, bacteria, fungus, whatever it is, coming back to the occupied zone? So what is the suggestion, and what is your opinion about this, sir?
As I understand it, your concern is the microbes collecting on the filter under humid environments where they might actually grow, particularly molds. However, if this is a portable UV filter unit, there should be some residual level of UV penetrating that filter and sterilizing it over time, since it gets 24-hour exposure. So it would seem that you should have very little problem at all with microbial growth on your filter if it's a part of the UV system.
Okay, understood. Thank you very much. I think I'm honored to get the good answer from your side. Thank you very much, sir.
Thank you for the good questions. Okay, are there any other questions here? I don't see any other hands raised. So if nobody has any other questions, and I've got a few minutes left to answer them, speak now or forever hold your peace. Oh, is this a question? Jim Fulbrook. Okay, Jim, what's your question?
Authorized his mic, so we should be able to speak.
Okay,
can you hear me?
Yes, we can.
Oh, very good. Okay, very good presentation. I admit I don't really understand all the aspects there about the performance testing. What it is you actually release in the air, and then, of course, obviously, it should have a period of time sort of circulating in the air. Then you're dosing it and all the rest, and then you have to collect it again and see that it's dead or, you know, inactivated. In other words, I don't really fully understand the whole notion of actually using a pathogen for a performance test. And then obviously that's still a controlled environment relative to like going into an actual hotel room, so a hospital room. So if you could just elaborate a little bit on that, I'd appreciate it. Thank you.
Okay. The standard means of determining the system efficiency, and this goes back, I think, at least 80 years, is the steady state UV system model. They build a room, typically 50 cubic meters. They inject a source, and that source may be Serratia marcescens, MRSA, Staph aureus, or any other microbe that is considered a target. But a lot of the tests are performed with MRSA or Pseudomonas or possibly Bacillus subtilis spores. The spores are injected at a high level into the room. They also die off at a high level because of oxygenation, air currents, etc., the stress of being aerosolized. But they achieve a steady state condition. Once that steady state condition is achieved, and it might take an hour, possibly two, to achieve steady state. Once the steady state condition is achieved, they turn the UV lamps on, and the kill rate manifests itself as a major reduction in room concentration. And it may take an hour, possibly two, to reach steady state again. But once that steady state condition is reached, it is a definitive condition and it represents the efficiency of the system, whether it's the efficiency across an induct system, across a portable unit, or across the upper room system. It's a classic test. It's very reliable, very reproducible, and the parameters we get are disinfection efficiency and airflow. There isn't another good way to run such a test other than measuring the inlet to outlet concentration, which will give you the same result. It will give you the same disinfection efficiency. So I hope that explains it pretty well. Is there any confusion left in regard to this model?
No, actually, that's very, very good. So, but if you did have a smaller type of device or something that was less restrictive, it seems to me that if you know what the output of the system is in your LED, and then you know what your airflow is, and that's well defined, that you still have a pretty good idea. And isn't that what a lot of people use for measuring things otherwise, is based on the history of how much is necessary, and if that flow rate is achieved, that you're going to get X amount of a kill rate.
Yeah, and like I mentioned, there are two kinds of tests. There's the in-room test we looked at, and then there's the induct test. The induct measures from point A to point B, that is from your inlet to your outlet. It directly measures the airflow and disinfection efficiency. And this works well for portable units and induct units. It's not so easy to apply for upper room or whole room systems. And for that purpose, we need the whole room model test. I hope that's clear.
Oh, absolutely. That really makes a big difference. Thank you.
Okay. Now, I'm going to try to start.
I think we reached the end of the presentation. Thank you, everybody, for attending, and I'll send you the link to view the presentation if needed. Thank you, Dr. Kowalski.
And thank you, everybody. Enjoy the rest of your Monday. Bye-bye.